In this lecture, we are going to look at a special kind of subgroup, the normal subgroup. Not all groups have non-trivial normal subgroups, but for the ones which do, we can actually use the normal subgroups to not only figure out a lot of important results about the group, we can actually use it to build an entirely new group out of the old one. This is called the quotient group structure. Both the normal group and the associated quotient group structure is going to play a huge role in physics as well as in representation theory. But before we go there, let me just recall some results that we had seen in the last lecture. Let me remind you that in the last lecture, we took a look at cosets. In particular, we looked at the example of the cosets with respect to a subgroup consisting of two elements E and A of the 6-element group of symmetries of the equilateral triangle. And we worked out both the left cosets, that is, some element G times capital H, and the right cosets, capital H times some element G of the group. And as you can see from this example, the cosets partition the group. They're either completely identical or disjoint. That's true for both the left cosets and the right cosets. But if you look at the two together, you find something rather striking. Notice that although the first two left cosets are the same as the corresponding right cosets, the other left cosets, say the left coset for B capital H, is not the same as capital HB, the right coset. And the same goes for all the other elements here. So, in general, as we found out then, left cosets and right cosets do not agree. However, we had also taken a look at cosets for another subgroup, which is the subgroup consisting of the three rotations, E, D and F. The 0-degree rotation, 120-degree rotation and 240-degree rotation. And in this case, as you can easily see, all the left cosets are exactly identical to the corresponding right cosets. So, for some subgroups, left cosets and right cosets are not the same, at least not all the same. But then there are some special subgroups for which left and right cosets are the same. And as we will see, these special subgroups are what are called normal subgroups. And that is what we are going to discuss in some detail in today's lecture. Let us begin our discussion on the normal subgroup with a bit of a detour. In the last lecture, we also met the concept of conjugacy. We saw that if you have a given element G1 of the group and some other element G of the same group, then G1, G inverse is an element which is conjugate to G1. Now we can use this concept of conjugacy not only to a single element, but to a collection of elements, maybe even a subgroup. So the first result that we are going to talk about today is this. If H is a subgroup of G, let me remind you once again that the less than sign here really stands for H being a subgroup of G. So the result that we are talking about is, if H is a subgroup of G, then for all small g belonging to capital G, if you form this collection H bar or set H bar, which is G capital H G inverse, that is, by definition, you take every element small h of capital H and form G small h G inverse and collect them all together. Then H bar is actually a subgroup of G. Not just a subset, it's also a subgroup. So let me first start by proving this. Well, the proof actually is pretty simple and it borrows on a result that we had in an earlier lecture, the theorem that we had proven there, which is if you want to prove that a subset capital H of G is a subgroup, what you need to show is that for all elements small h1 and small h2 belonging to capital H, h1, h2 inverse also belongs to capital H. So we are actually going by that. We already know that capital H is a subgroup of G. What we are trying to do is prove that capital H bar is also a subgroup of G. So we start with two elements, h1 bar and h2 bar, which belongs to capital H bar, this subset. Now from the definition of capital H bar, it's obvious that there must exist two elements small h1 and small h2 in capital H such that small h1 bar is G small h1 G inverse and small h2 bar is G small h2 G inverse. So let us try to use our theorem for subgroups with h1 bar and h2 bar as two arbitrary elements of the set capital H bar. So let us form h1 bar h2 bar inverse. Now since h1 bar is G h1 G inverse and h2 bar is G h2 G inverse, this is exactly what we are talking about. But now we use the fact that G h2 G inverse is inverse using the standard rule that AB's inverse is B inverse A inverse turns out to be G h2 inverse G inverse. So that's what we have. But now we can use the associativity property which is there in every group to change the brackets and put a bracket around G inverse and G, which means G inverse and G will just cancel each other out. So we will be left with G h1 h2 inverse G inverse. Now h1 h2 inverse of course has to be an element of capital H. So this h1 bar h2 bar inverse is an element of capital H bar. And that completes our proof, because remember our theorem told us that if you take two arbitrary elements h1 bar and h2 bar from capital H bar and manage to prove that h1 bar h2 bar inverse is also in capital H bar, then capital H bar must be a subgroup of G. We can call H bar a conjugate subgroup to the subgroup H. Now the reason why this notion of a conjugate subgroup is so important in the context that we have been discussing is that any left coset of the subgroup H is actually a right coset of the subgroup H bar. In particular, it's easy to see that GH equals H bar G. Now this equation looks like all you have done is you have taken GH G inverse equals H bar and hit it on the right by G, and the G inverse and G have cancelled to give you GH equal to H bar G. Frankly, that's not exactly an accurate way of doing things, simply because in the ultimate analysis, these products are defined between elements and not really between whole subgroups. But it should take you a very little thought and maybe a bit of pen on paper to convince yourselves that you can actually calculate things this way. If the set H bar is GH G inverse, then the set GH is H bar G. Now if small g happens to be a member of capital H itself, then it is easy to see that small g capital H G inverse is actually H itself. But in general, if small g happens to be an element of the group capital G, which is not in capital H, then it's quite possible that small g capital H G inverse will be some other subgroup of capital G. However, there are special subgroups for which small g capital H small g inverse always turns out to be the same as capital H, irrespective of whether small g belongs to capital H itself or not. And such subgroups are actually called normal subgroups. So let me come to the formal definition of a normal subgroup, which is just a repeat of what I said right now. A subgroup N of a group G is called a normal subgroup of capital G if, for all small g belonging to capital G, G is a normal subgroup of capital G. If, for all small g belonging to capital G, G is a normal subgroup of capital G. If, for all small g belonging to capital G, G is a normal subgroup of capital G. If, for all small g belonging to capital G, G is a normal subgroup of capital G. If, for all small g belonging to capital G, G is a normal subgroup of capital G. If, for all small g belonging to capital G, G is a normal subgroup of capital G. If, for all small g belonging to capital G, G is a normal subgroup of capital G. If, for all small g belonging to capital G, G is a normal subgroup of capital G. If, for all small g belonging to capital G, G is a normal subgroup of capital G. If, for all small g belonging to capital G, G is a normal subgroup of capital G. If, for all small g belonging to capital G, G is a normal subgroup of capital G. n is the same as G n G inverse. And here you just have a reminder of what G n G inverse means. It of course means the same thing as the conjugate subgroup that we saw right now. Is simply the collection of all elements of the form small g, small n, small g inverse as small n runs over the entire subgroup capital N. Of course, I have called this subgroup capital N instead of capital H simply to signify that we are talking of a normal subgroup. Now, one more important thing. We have already seen that the less than sign is actually used to denote a subgroup. But this sidewise turned triangle sign is actually used to denote that N is a normal subgroup of G. Because normal subgroups are going to play a very important role in what is going to come, it's important that you be pretty well versed in the various properties, special properties, which normal subgroups have. Now, one very special property which normal subgroups have is this. If capital N is a normal subgroup, then its left cosets and right cosets are identical. Now, this is trivial from what we had in the last slide. Remember, if H bar is G H G inverse, then small g h, the left coset of capital H with respect to small g, must be the same as H bar small g, that is the right coset of H bar with respect to small g again. Now, since this definition tells you that capital N is conjugate to itself, no matter which small g you use, you always end up with small g capital N equals N cap small g. And therefore, for a normal subgroup, the left cosets and right cosets have to be identical. Now, it's actually rather simple to prove that the converse is also true. If you have a subgroup capital N of a group capital G, such that for all small g in capital G, small g capital N is the same as capital N small g, then capital N has to be a normal subgroup. And the proof of this converse statement is rather trivial. Now, no matter what your group is, the group will always have two normal subgroups by default. One of them is the trivial subgroup, which is the identity alone. It's easy to see that if you take any small g and use that on the subgroup with E alone, you're going to get a single element group which has the element small g E small g inverse, which of course is again the same subgroup back. So this trivial subgroup is definitely a normal subgroup of every group. And then there's another group which is always a normal subgroup of every group, which is the group itself. Because it's rather again very trivial that you would take small g from the group and do small g capital G small g inverse, you're going to get capital G back every time. So these two subgroups are normal subgroups for every group. And these are called the trivial normal subgroups. Now, this actually brings us to a very important concept. A group is called simple if these are its only normal subgroups, which means a simple group has no non-trivial normal subgroups. The notion of a simple group and its relaxation, a semi-simple group, is going to be very important when we talk about group representations. But for the time being, this is something which is an important definition. A simple group is one whose only normal subgroups are the two trivial normal subgroups. The trivial subgroup with the identity alone and the whole group. In a sense, abelian groups are the exact opposite of simple groups, since every subgroup of an abelian group has to be a normal subgroup. That's trivial from the definition. That is not to say that an abelian group cannot be simple. For example, a group of prime order is abelian, as we had seen in a previous lecture. This result follows simply from Lagrange's theorem. On the other hand, a group of prime order is abelian precisely because it cannot have any non-trivial subgroup. So it of course cannot have a non-trivial normal subgroup. So a group of prime order is both abelian and simple. Now this is an important result that we have on your slides right now. We often need to prove that a subgroup capital N of a group G is normal. It turns out that it is enough to show that for all small g belonging to capital G, the set small g capital N small g inverse is a subset of capital N. It's contained in capital N is all you need to show. Why this is enough is again rather simple. Remember, this has to be true for all small g belonging to capital G, which means it also has to be true for small g's inverse. So, the moment you show that for every small g in capital G, G inverse is a subset of capital N, you end up also showing that G inverse capital N G is a subset of capital N. That means simply that N is a subset of G inverse. Now, as you have learned from elementary set theory, the easiest way to prove that two sets are equal is to show that each one is contained in the other. Here, if you manage to show that small g capital N small g inverse is contained in capital N for all small g, then as I have just shown, it trivially follows that capital N also is contained in small g capital N G inverse. So these two have to be equal and hence capital N has to be a normal subgroup. Let us now take a look at a few examples of normal subgroups of some bigger groups. Our first example is the one with which we started today's lecture. We are considering the group S3, which is formally the set of all permutations of three objects. But the example that we have seen is a set of symmetries of an equilateral triangle. And as we have seen, that's essentially the same group as the one which permutes three objects, namely the vertices of the equilateral triangle. Now, in the example which we began with, we saw distinctly that the subgroup consisting of the identity and a reflection, E, A, had different left and right cosets in general. On the other hand, the subgroup which consisted only of the three rotations, E, D, and F, actually had exactly the same left cosets as right cosets for every element small g. So EDF is a normal subgroup of the group S3. In our next example, we are going to take a look at a bigger group, GLNR, the set of all n by n invertible real-valued matrices. The claim that I am making is SLNR, the subgroup which consists only of those matrices which have determinant 1, is a normal subgroup of GLNR. Now let us prove this statement. To prove this, what we need to show is basically that for all M belonging to GLNR, that is for all invertible n by n real valued matrices, M SLNR M inverse is the same as SLNR. To show that, let us pick an element S bar from M SLNR M inverse. Now, if this is true, that if S bar really belongs to M SLNR M inverse, then there must exist some S, some matrix S in SLNR such that S bar is MS M inverse. Now, all we have to do is check what the determinant of S bar is. Now, the determinant of S bar from elementary matrix theory is determinant of M S M inverse, which is determinant of M times determinant of S times determinant of M inverse, determinant of M and determinant of N inverse are reciprocals of each other, so they always cancel out. Determinant of S is 1. So when you use that, you end up with the statement that det S bar is actually 1. And this implies that S bar is actually a member of SLNR. So every element of M SLNR, M inverse, is in SLNR. So all we have shown here is that M SLNR, M inverse, is a subset of SLNR for every M in GLNR. And remember, that's all you really have to show that SLNR is a normal subgroup. That is, M SLNR, M inverse is equal to SLNR for all M. The final example that we are going to take a look at is in a way related to the previous two examples. Here the group is O3, the set of all rotations and reflections in 3 dimensions, or in more mathematical terms, the set of all 3 by 3 orthogonal matrices, and the subgroup that is also a normal subgroup is SO3. SO3 is the set of all 3 by 3 orthogonal matrices with determinant 1. It also happens to be the set of all rotations in terms of actual things that you do on the real world. I will let you wonder why I said that this is related to both of the previous examples, although it's really not too hard to figure out. As we have said earlier, the existence of normal subgroups of a group leads naturally to a construction of the quotient group, which is in a way a method of sort of identifying some elements of a group and treating them together as a single element, as we will soon see. But as a way of starting slowly towards building up the notion of the quotient group, we will start with the notion of the product of subsets. Now, if A and B are subsets of capital G, you can easily define their product by doing the obvious thing. Capital A times capital B is defined to be the set of all elements small ab, where small a belongs to capital A and small b belongs to capital B. That's the only natural definition that you can really give to the product of two subsets. Now, cosets of a subgroup are, of course, subsets of the supergroup. So we may ask a question about forming a product of the cosets. And since this is a product operation, a natural thing to ask would be, can we make a group out of this? So can cosets for a subgroup form a group under this kind of multiplication? And the answer to that in general is no. As you can see very easily, the product of two cosets is not a coset in general. As a result, this multiplication is not a binary operation on the set of cosets, or in another language, the set of cosets is not closed under this multiplication. To see this, let us go back to the example of S3 and take as a subgroup the group consisting of the identity and a reflection E, A. Now this has two cosets, AH, which is EA. By the way, you could label the coset as AH and equally well as EH. And let's take another coset, BH, which consists of the elements B and F. And as always, you could also write this coset as FH. But now let's try to multiply these two cosets together and see what will come out of it. So the product of the two cosets that we are looking at is AH times BH, which is the product of the set EA with the set BF. And as we defined above, what we have to do is take every element of the set on the left and multiply them by every element from the set on the right in succession. So you end up with 4 elements, EB, EF, AB and AF. Of course, it's possible that these 4 elements will turn out to be not really 4 distinct elements, and because this is a set, we will just ignore repeated elements. But anyway, It turns out that if you use the multiplication table, this particular collection of 4 elements are actually 4 distinct elements. The first 2 are obvious, they are B and F. The next 2 happen to be D and C, as you can easily verify from either the multiplication table or just by following the multiplication operation on a picture of the triangle. Now it is obvious that the result that you have here is not a coset for the subgroup H, simply because all cosets of the subgroup H must have the same number of elements as the subgroup H, namely 2, and this one obviously has 4. In fact, since no subgroup of S3 can have order 4, remember Lagrange's theorem insists that the order of a subgroup has to divide the order of the group, and 4 obviously does not divide 6. BFDC, the result that we have, cannot be the coset not only for this particular subgroup but for any subgroup. Well, frankly, that last thing was a bit of an overkill. All you really needed to show was that this is not a coset with respect to H. Now this is a bit of a disappointment. Note that our actual aim here is to club elements of a group together, that is, partition the group into unique pieces and try to define a multiplication rule between those pieces in a natural way. Now since cosets are equivalence classes with respect to the equivalence relation congruency modulo a subgroup, they provide us with a very nice way of partitioning the group. So it would have been great if the cosets could be multiplied to provide a group structure. Now, while we have just found that for an arbitrary subgroup, the cosets cannot be multiplied to give further cosets, it turns out that cosets can be multiplied to give cosets if the subgroup happens to be a normal subgroup. So we now turn to that point. What about product of cosets, which are cosets with respect to a normal subgroup of a group? So the statement that we are making at the very outset is this. If N is a normal subgroup of G, then for all G1, G2 belonging to capital G, the coset G1N, when multiplied by the coset G2N, according to the rule of multiplication which we have just now laid out, gives rise to a coset, which is the coset G1, G2N. Now let me point out one thing. If this statement is at all true, then the coset, which is the result of multiplication of G1N by G2N, has to be the coset G1, G2N. Simply because G1N definitely contains G1, G2N definitely contains G2. After all, N being a subgroup has the identity in it. So G1N times G2N has as one of its elements G1, G2. And so if it is going to be a coset at all, it has to be a coset in which the element G1, G2 belongs. And that of course is a coset of G1, G2 with respect to N. So G1, G2, N. Now that of course is true provided the result is a coset in the first place. What we now need to show is that this really is correct. That is, the product of G1N and G2N, two cosets with respect to a normal subgroup, is also a coset with respect to the same normal subgroup. And the proof of this goes as follows. We start by taking an arbitrary element from G1 and G2N. Of course, if X belongs to this element, then X must be of the form G1, N1, G2, N2, where N1 and N2 are elements of capital N. So there must exist such elements N1, N2 in capital N. What I need to show is that X also belongs to G1, G2, N. That's the first thing that we need to show here. Now, in order to do that, what we will do is we will write X, which is G1, N1, G2, N2, and try to write it as G1, G2 times an element of capital N. And the way to do that would be simply to put in a G2, G2 inverse, which is of course the identity, in between G1 and N1, in the expression above. So this is what we do first. Of course, this thing using the associativity law is the same as G1, G2 times G2 inverse N1, G2 times N2. Now G2 inverse N1, G2 has to be an element of the normal subgroup capital N. This is what being a normal subgroup means. By the way, another name for the normal subgroup is an invariant subgroup, and this is the reason behind that nomenclature. What that means is, of course, if you take any element in capital N and conjugate it with any arbitrary element of the group, you are going to get an element of capital N again. So this is some element N1 prime of capital N, but now what you have is N1 prime times N2, which, being a product of two elements of capital N, has to be an element of capital N. Here all we have used is the fact that capital N is a subgroup. And this goes to show that X is G1, G2 into some element of capital N, so it has to belong to the coset G1, G2 capital N. So as an upshot of all this, what we get is every element in G1n, G2n is an element of G1, G2n, and thus G1n, G2n has to be a subset of G1, G2n. Now the other inclusion, that is G1, G2n is included in G1n, G2n, is rather trivial, so I will just leave you to worry about how to prove that. But because the inclusion is both ways, we get the result that G1n times G2n is G1, G2n. So the product of two cosets with respect to a normal subgroup is another coset, and in fact the multiplication rule here is very simple. If the first coset corresponds to the element G1 and the second coset corresponds to the element G2, then the product coset corresponds to the element G1, G2. At this stage, you may have a bit of a doubt about which element does a particular coset correspond to. And this is very easy to see. Instead of saying that a particular coset is G1n, that is, it corresponds to G1, you could take any other element, let's say G1 prime in that coset, and call that coset G1 prime n. So the group element that you use to label a particular coset is not unique. Any element from a given coset can be used to label that particular coset. This is true irrespective of whether the subgroup is a normal subgroup or not. I will let you worry about why this is consistent with the product law that we have written down here. That is, instead of taking G1 as a label corresponding to G1n, if I had taken G1 prime, which is some other element in G1n, and instead of taking G2 as a label corresponding to G2n, I had taken G2 prime, then of course my rule would have ended up telling me that the product is G1 prime, G2 prime n. What you need to worry about is why G1 prime, G2 prime n is actually exactly the same coset as G1, G2 n. This is really rather simple to prove, but still is something which you have to figure out yourself. We have now crossed the first hurdle on the way to defining a group using the cosets. We have seen that the product of cosets for an arbitrary subgroup is not a closed operation. That is, it does not necessarily yield another coset. However, as we have just now proven, if the subgroup happens to be a normal subgroup, then the cosets with respect to a normal subgroup, when multiplied, does give you another coset corresponding to a normal subgroup. So at least we have a chance that under this particular multiplication rule, cosets corresponding to a normal subgroup may end up forming a group on their own. So let us actually check whether that is true. So what we are claiming is the set of all cosets written G by n. So that's the notation. Quotient group, that's a name. So G by n is the notation for it, which is the set of all cosets small g n as small g runs over the entire capital G. Of course, when small g runs over the entire capital G, you do not get distinct cosets, you just get a number of cosets. Now these cosets, given that n is a normal subgroup of G, form a group under the multiplication of sets. This is my demand. So let us try to prove that that is true. Of course, this means that we have to check all the properties of a group for this particular set. And of course, using the rule that we have already imposed for multiplying sets. Okay, so we have already seen that G1n, G2n is G1, G2n, which is a member of G by n, this underlying set. So G by n is closed under this product. So closure is done. Now what about associativity? Well, what we do is we try to show that the bracket doesn't matter in a product like this, in G1n times G2n, G3n. But according to the rule that we have just figured out, G1n, G2n, G3n is nothing but G1n, G2, G3n. And that rule can be applied again to see that this is G1, G2, G3n. Now we are at the arena of the group G. So this product here between G1, G2 and G3 is a product that you are already aware as an associative one because it's a product of a group G. So this is the same as G1, G2 bracket G3n, and this, by using our rule in reverse, is G1, G2n times G3n. So it's G1n, G2n times G3n. The bracket can be shifted from here, the last two elements, to the first two elements, which is exactly what associativity means. So this particular product is an associative one. We next have to show that the set G by n has an identity under this particular rule for multiplication. The identity is very easy to identify, is the coset En, which of course is the same as the subgroup n itself. Now how do we prove that this is the identity? Well, all you have to do is check whether for all Gn which belongs to G by capital N, G capital N, E capital N is the same as E capital N, G capital N is the same as G capital N. This is rather trivial from the rule that we had worked out. After all, Gn, En is simply Ge times n, and Ge is of course G. That's sort of obvious from the group multiplication rule. Now the final hurdle that we have to cross is the existence of an inverse for every group element. So the inverse of Gn, a coset, is simply the coset corresponding to the inverse element of G. So small g inverse capital N, which also is a coset, so it belongs to the set G by n, is claimed to be the inverse of Gn. And that's very easy to check. All you have to do is multiply G inverse n Gn or Gn G inverse n. I've just shown the last line, but you can easily check that this works also for the thing on the left here. Gn G inverse n is Gg inverse n, and Gg inverse of course is identity, so this is En. Sorry, there's an equality sign which has gone missing here, and En has to be equal to n. So the existence of the inverse has been established. This completes our proof that the set of all cosets with respect to a normal subgroup n of G forms a group in its own right under the multiplication of sets. This group G by n, remember we label a group and the underlying set similarly very often, and that's what we have done here. The group G by n is called the quotient or factor group. The nomenclature here is sort of obvious. G by n is written with a division sign, so the quotient or factor. This nomenclature seems to be sort of the obvious thing to use here. Now let us finish with a few examples of the quotient group. The first example that we will talk about will involve the group S3 and its normal subgroup, the group of the three rotations E, D and F. Remember, we do need a normal subgroup in order to be able to define a quotient group. So what we are going to now try to find out is what is S3 divided by n, or S3 quotiented by n. Now for this, what are the elements of S3 quotient n? The elements are simply the two cosets. Why 2? Remember, the number of distinct cosets a particular subgroup has for a finite group is simply the order of the group, in this case 6, divided by the order of the subgroup, in this case 3. So there are just two cosets which can be labeled as En and An. En is of course n itself, EDF. By the way, you could have labeled it equally well as Dn or Fn. And An has the elements A, B and C, and it could have been labeled either An or Bn or Cn. But let us stick to En and An here. Now, we have already established that the quotient group is a group. And even without going any further, we can tell you what group this is, because this group has only two elements, and as we had worked out in an earlier lecture, there is really only one group with two elements. So the multiplication table can simply be written down without any hesitation. It has to be this particular multiplication table. I will ask you to verify for yourselves by explicitly multiplying out these two sets that this multiplication table is really satisfied in this case. Our next example is going to be a bit more non-trivial. Of course, once again we need a group and we need a normal subgroup for that group. So we are going to take as an example GLNR as the group G and SLNR as its normal subgroup. So what we are trying to find out is the quotient group which you get when you quotient out GLNR by SLNR. How do we characterize a coset of GLNR with respect to SLNR? Well, we start by asking the question that if a matrix M prime belongs to the coset M times SLNR, so a particular element of the quotient group in this case, if M prime belongs to that element, what actually does this tell us about M prime? Of course, the first thing it says is that there must be a matrix S in SLNR such that M prime is equal to M times S. However, we can also say something simpler. A matrix M prime belongs to the coset M SLNR if and only if determinant of M prime, of course, equals determinant of M times S, which is determinant of M times determinant of S. And since S is a member of SLNR, its determinant is 1. So this has to be the same as determinant of M. So this, of course, shows that if M prime belongs to M times SLNR, then det M prime has to be equal to det M. What we need to also show is the converse, that if det M prime is equal to det M, then M prime belongs to this coset. Now that actually is very easy to show. It just uses the fact that M prime and M are both elements of GLNR, so they are both invertible matrices. And it follows rather trivially that the matrix M inverse M prime belongs to SLNR because it has determinant 1. So M prime has to be M times the matrix in SLNR, and so M prime has to belong to this coset. So the statement is not just only if, it's also if. If and only if, both sides. Now, what this helps us to say is that the value of the determinant actually characterizes a coset. You can take all the matrices in a coset and lump them together by just telling me what the determinant of any one element of this coset is, because all other matrices in that coset will have exactly the same determinant. Actually, things work the other way round as well. If you give me any real number as the determinant of a matrix, then I can find for you the coset of SLNR, which is labeled by that real number. All you have to do is find one matrix with that determinant, and that matrix is going to label a whole coset, which is that matrix times every element of SLNR. And that particular coset will have only matrices with that particular determinant. Well, I was a bit too hasty in saying all possible real numbers a while ago, because as you can obviously see, there's one real number which is excluded from this set, and that real number is 0. Since all the matrices here are members of GLNR, they're all invertible, so they cannot have a determinant of 0. By the way, in order to fully establish what I said right now, you have to show that given any non-zero real number, you can find an n by n matrix with that determinant. But that is such a trivial thing that I am sure that everybody can work that out. Now, what about the product of two cosets? If you take the coset m1s and multiply it by the coset m2s, you are going to get the coset m1 m2s. But the first coset is labelled essentially by the determinant of m1, the second coset is labelled by the determinant of m2, and the product is labelled by the determinant of m1 m2. So basically the labels, which are just non-zero real numbers, they are getting multiplied in this multiplication rule. So the group GLNR by SLNR is essentially the same as a group of non-zero real numbers under multiplication. Now this statement, essentially the same, requires some further elaboration because we have not really defined what it means to say that two groups are really the same. Well, we have sort of used the notion that two groups are the same if they have the same multiplication table. That is, if you relabel the entries, you can actually replace one multiplication table by another. However, we need to still formally define what this notion means. And that is what we are going to do in the next lecture.